Hello dear students. So today in this lecture we are going to talk about the problems on chapter study of transistors. So we already saw the concepts related to transistor, its functioning. Now we are trying to understand how to solve the problems related with the chapter study of transistor. So we are going to talk about the first problem. See, here it is. There it is a circuit. A change of 250 millivolt in base emitter voltage causes change of 125 microampere in the base current IB. Find out the input resistance Ri of the transistor. So we already know this is the circuit which shows that here it is. This is a base, this is emitter, and this is collector. So here it is. This is base, emitter, and collector, and the problem is that we have to find out the input resistance Ri. So this is input side, in which this is a battery. Here it is, base current IB is flowing and voltage across base emitter junction is VB. So we know that according to Ohm's law, V is equal to IR. So in order to find out the resistance is equal to V upon I. But at this input side, the applied the voltage is VBE and the current flowing is IB. So as in problem, we have given the change of 250 millivolt in base emitter voltage. That means VBE is changing to 250 millivolt, and so here it is, a change of 250 millivolt in base emitter voltage. That means change in this VBE is 250 millivolt and base voltage causes change of 125 microampere. So that is change in IB, and so here it is, putting the values, that is delta VBE is equal to 250 millivolt, 250 millivolt, milli means into 10 raised to minus 3 volts, divided by the corresponding current change in IB, that is 125 microampere. So that is 125 into 10 raised to minus 6, and from this we get the resistance value is 2 into 10 raised to 3 ohm, that is equal to 2 kilo ohm. So this way we can solve this. So second problem, find the value of beta. That is, note down, it is a current gain beta if alpha is equal to 0.9 and second alpha is equal to 0.99. So first important thing that we already saw the beta and alpha. Alpha is a current gain, that is output current IC divided by input current IE. That ratio is called as alpha. Beta is IC upon IB. So here there it is a relation between emitter, collector and base, that we know that IE is equal to IC plus IB. So for problem solving you must know it. So here remember that IE is always equal to IB plus IC, that it is shown. So here we have to find out the value of beta where alpha is given. So the relation between beta and alpha, in order to find out beta is equal to alpha upon 1 minus alpha. So just simply putting the value 0.9 in place of alpha, here beta is equal to 0.9 divided by 1 minus 0.9, that turns to be 9. So here beta is equal to 9. Similarly, we can find out beta. So here the second value of beta is 0.99. So you can say that is beta is equal to alpha upon 1 minus alpha. So that is equal to 0.99 divided by 1 minus 0.99, and that is equal to 99. So this way we can find out the value of beta. So remember the relation between beta and alpha, and the relation that is beta is IC upon IB and alpha is equal to IC upon IE for further problem solving. Okay, thank you. See the problem third. In common emitter configuration of transistor. So we know that in case of common emitter configuration, input current is base current and output current is collector current. See here, if it is the transistor in which this is an emitter which is common, so this is input side, this is base, and here the output side, that is collector side. So here emitter is common, so here it is base current IB, and here in this base current collector current IC flows, and we know that IB is equal to I is equal to IB plus IC. So here the common emitter configuration, the change in collector current IC is 2 milliampere. So here current changes by 2 milliampere. For the change in the base current IB, that means when this IB is changed by 10 microampere, the corresponding change in IC is 2 milliampere. So this is the relation. So find the base current amplification factor. So we know that base current amplification factor is beta is equal to IC upon IB. So we have a change in IC, that is delta IC is 2 milliampere and delta IB is equal to, so therefore beta is equal to delta IC upon IB. So here delta IC is given, that is 2 into 10 raised to minus 3, that is 2 milliampere, and change in delta IB is given 10 into 10 raised to minus 6, and so therefore we get the value of beta, that is equal to 200. So this way we can solve this problem. So next problem, see, for as shown in figure, for a transistor shown in figure, the voltage drop across 2 kilo ohm resistance. Remember this is 2 kilo ohm resistance which is connected to collector, that is output side. So voltage drop across this resistance is 1 volt. So that means voltage drop Vc across this, it is 1 volt. Remember that. And we know that this voltage is equal to what? This resistance into the value of collector current. So voltage is known, resistance is known, we can easily find out the collector current since V is equal to IR, I is equal to V upon R, that is Vc upon RC. If beta is equal to 50, find the base current. So we already know beta is equal to what? It is a current gain factor IC upon IB. So beta is equal to IC upon IB. So things are there. We need to first find out IC since resistance and voltage is known. So IC is equal to Vc upon RC. So here we got the value of IC, but beta is given. So from this relation we can find out IB is equal to IC upon beta. So here IC is equal to Vc upon RC. Voltage across this Vc is given 1 volt divided by the value of resistance RC, that is 2 kilo ohm, that is 2 into 10 raised to 3 ohm. So here we get the value of current IC, that is 0.5 milliampere. So this is value of IC. Now we know the value of IC. We know the value of beta that is given. So we know beta is equal to IC upon IB. So therefore beta is equal to IC upon IB is equal to IC upon this. So here collector current, that is 0.5, it is milliampere, means it is 10 raised to minus 3 divided by the value of beta given, that is 50, and the value of IB which we get, that is 10 microampere. So in this way we can solve this problem. So next problem, calculate the values of three currents in the common emitter circuit shown in figure. So here we know it is a common emitter circuit. Okay, this is common emitter. So it has three currents, that is collector current, base current and emitter current. So the things which are given in the circuit are, first VCC is equal to 20 volt. So we know that we need to recall the relation, that is this is VCC, that is given 20 volt. Okay, so thereafter here it is the RC is given 2 kilo ohm and we have to find out IC. Okay, so that is one important thing. Thereafter here it is RB is given, we have to find out IB. So voltage across RB is IB into RB, that you know. Voltage across RC is equal to IC into RC. So here beta is given, that is 100. The resistance RE is 1 kilo ohm and we have to find out the emitter resistance. So the given things are that VCC is given 20 volt, then RB is equal to 2 mega ohm. 2 mega ohm means what? 2 into 10 raised to 6 ohm. Then RC is given, here it is RC, that is equal to 2 kilo ohm. And RE is given, that is, this is 1 kilo ohm. So these are the given things, and apart from that beta is given. So beta is we know that is the relation IC upon IB, and that is given, its value is 100. So these are the given things. Now see, according to applying Kirchhoff's law to the base side circuit. So see, this is base side circuit, this is emitter side circuit. So according to Kirchhoff's law, that applied voltage must be equal to voltage across RB, then voltage across base emitter, and voltage across RE. So therefore we can say VCC, applying, remember that we are applying the Kirchhoff's law to base side, VCC is equal to, the current flowing through this is IB. Okay, so IB into RB, that is IB RB, plus voltage across base and emitter, that is we call it VBE. So plus VBE plus here IE into RE. So current flowing through this. So this is one relation which we already saw. Okay, if VB is very small, we can consider that VB is 0. It is very, very small. So therefore, if VBE is very small, that is equal to 0, let us consider. So therefore we can say that is VCC is equal to IB RB plus IE RE. So that relation we get. So here second important thing, that we know that emitter current is always equal to base current into collector current. So we know that IE is equal to IB plus IC, and we already saw beta is relation, that is beta is the relation between IC and IB, that is beta is equal to IC upon IB. So therefore from this we can say IE is equal to, okay, so here can we, here IC is equal to beta times IB. Okay, we can write that. From this we can say IC is equal to beta times IB. Okay, so if you use this term here, so we get it is IB plus beta times IB. That means now instead of three different currents, we got the relation between two currents. This is what the value of IE. So now we have already this relation VCC is equal to IB RB plus IE RE. But we saw IE is equal to IB plus beta times IB. So we are putting this value here. So we get VCC is equal to IB RB plus this value of IE here plus IB plus beta times IB into this value RE. Okay, so we know the value of VCC, that is equal to 20 volt, that is equal to. So here we already have the value of RB and value of RE. So just putting that value there, that is here it is IB into value of RB, that is 2 into 10 raised to 6. See here it is RB is equal to 2 into 10 raised to 6, RC is equal to 2 kilo ohm and RE is equal to 1 kilo ohm. So putting that values plus here it is IB plus beta times IB into RE. So value of RE we already know it, or here we can take IB common, that is we get 1 plus beta. Okay, this turns into this and into this value of RE. So here it is 1 plus beta, that we know, so that we can say IB plus into 2 into 10 raised to 6 plus beta plus 1, beta is 100, so 100 into here beta plus 1 is equal to 101 into the value of RE, that is 1 kilo ohm, that means 1 into 10 raised to 3, so that is 10 raised to 3 into the value of current IB. So here we get the value 2.101 into 10 raised to 6 into IB. So that is equal to 20. So therefore from this we get IB is equal to 20 divided by this term, that is 20 divided by 2.101 into 10 raised to 6, and that turns to be 9.52 into 10 raised to minus 6, or we can say 9.52 microampere. So this way we have got the value of IB. Okay, so IB is now known and beta is also known. So from this, since beta is equal to IC upon IB, we can say IC is equal to beta times IB, and here it is beta is 100 into IB, that is 9.52 into 10 raised to minus 6, and therefore IC is equal to 0.952 milliampere. So this is the current which we have got, and we know relation, that is IE is equal to IC plus IB. So just putting the values of IC and IB, so we get the value of IC is 0.952 into 10 raised to minus 3 plus the value of current IB, that is 9.52 into 10 raised to minus 6, or we can even write like this: 0.952 into 10 raised to minus 3 or milliampere, plus we can say 0. We are converting micro into milliampere, 0.0952 into 10 raised to minus 3, and this way we get emitter current IE is equal to 0.96152 milliampere. So this way we got IE, IB and IC. So note down that problem is calculate the values of three current, that is IE, IB and IC. We know the relation that I is equal to IB plus IC, and simply by using Kirchhoff's law to the base circuit we can find out, we got this relation, and from this we can find out the IE, IB and IC. So see, the problem is determine the base current and collector current in the following circuit in which silicon transistor is biased using feedback resistor method. So remember that we have to find out base current and collector current. So base current, this IB we have to find out, and the collector current we need to find out. Okay, the important thing to be noted, silicon transistor used means what? Its threshold voltage, knee voltage is 0.7 volt, that you remember, is biased using feedback resistance. Now see, whenever we have to find out the base current, so from this figure what things are given, that let us consider that VCC is given 10 volt, that is first thing. Then RC is given collector resistance, that is 1 into 10 raised to 3, that is 1 kilo ohm. RB is given, that is 50 into 10 raised to 3 kilo ohm, 50 kilo ohm. Beta is equal to 100, and we know that beta is nothing but IC upon IB, that remember very well. And here the emitter. Now in order to solve this problem, we have to first find out the things which are given, that is feedback resistance value we know, that RB. So note that we know V is equal to IR relation, so therefore R is equal to V upon I. So now we are talking about the resistance RB. So whenever we are talking about RB, so what is potential drop across resistance RB, that is to be calculated or understood, and current IB which we need to find out. So when we talk about voltage across RB, remember that VCC, when it is applied, sum of the voltage is divided across this RC. Okay, so voltage across RC, that is ICRC. Okay, sum of the voltage is dropped across RB, that is IB RB, and remaining voltage is dropped between base and emitter, that is VBE. So that you should voltage drop across this is VBE. Okay, so here voltage drop across this, it is IB RB, and voltage drop across this is IC RC. Now if we apply the Kirchhoff's law to this base circuit, you will see that VCC is exactly equal to this voltage plus this voltage plus this voltage, and we know here it is RB. So we can say RB is equal to, we can write RB is equal to, so what is voltage drop across this? Remember that VCC minus this voltage minus VBE. Okay, so remaining voltage will appear across this. See, VCC is addition of this voltage and this voltage. Okay, so voltage across this means what? The voltage, see, VCC minus VBE minus ICRC. Okay, so here it is VCC. So that is voltage appearing across base resistance and divided by the current IB. So here from we can say that the resistance value RB is VCC minus VBE, but we know that IC is beta times, see, beta is equal to IC upon IB, so IC is equal to beta times IB. So we can write beta times IB into value of collector resistance RC divided by the current IB. So from this we can write IB RB is equal to VCC minus VBE minus beta times IB into RC. So remember that RC is given, that is 1 kilo ohm. VBE is known, that is for silicon it is 0.7 volt. VCC is known, so we have these three values. We have to calculate IB. So putting those value here, value of RB is, that is IB into value of RB, that is 50 into 10 raised to 3, 50 kilo ohm, that is equal to VCC, that is 10 volt minus VB 0.7 volt minus beta times IB, value of beta is 100 times IB into RC, that is 1 kilo ohm. So here it is VCC 10, VB 0.7, beta times IB into RC is 1 kilo ohm, that is 10 raised to 3. So that is equal to 9.3 minus 10 raised to 5 times IB. So 10 minus 0.7, that is 9.3 minus, that is equal to IB into this. So from this we can say so here it is IB into 50 kilo ohm minus this minus, so minus it becomes plus, plus 10 raised to 5 times IB is equal to 9.3, and from this we can find out the value of IB is equal to 9.3 divided by 1.5 into 10 raised to 5, this total is there, and that is equal to IB is equal to 6.2 into 10 raised to minus 5 ampere, or we can say that is equal to 62 micro ampere. So we got the value of IB, that is 62 micro ampere. So we already know that is IC is equal to beta times IB. So just putting the values, we get beta is equal to 100 into 6.2 into 10 raised to minus 5. So therefore IC is equal to 6.2 milliampere. So in this way we can find IB and IC. Okay, thank you. So now let us consider the problem. Let's see, figure shows the voltage divider bias method. So here we know that this is voltage divider, resistance R1 and R2 at point A is connected to base and it is dividing the voltage, so it is voltage divider method. So here determine the ammeter current. So you want to find out the IE. So in order to find out IE, you should think about IB and IC, and draw a DC load line and find operating point, that is a Q point. So see, first important thing, we already know what is DC load line. Understand the concept. Here when we talk about finding the DC load line, here it is the plot of VCE and collector current. We already studied it, okay, and there are 2 points we join. There it is a line, this is called as a DC load line, and here we get somewhere that is a Q point, that is zero signal collector current and collector emitter voltage. So we have to find out this, that is first thing. So we have to draw this DC load line. So we must know the voltage VCE when ICE is 0, and when VCE is 0, what is the maximum current that we want to find out in this circuit. So that is, so let us consider what things are given. So here from figure we see that VCC is given, that is 15 volt. Then RC, this is 1 kilo ohm, that is 1 into 10 raised to 3 ohm. Thereafter R1 is 10 kilo ohm, that is R1 is equal to 10 into 10 raised to 3 ohm, that is given. Then R2 is 5 kilo ohm. R2 is equal to 5 into 10 raised to 3 ohm, and as it is a silicon transistor, voltage across base emitter, that is VBE, is equal to 0.7 volt. So these things are given. So now let us find the voltage across resistance R2. So see, remember that voltage across R2 when we have to find out. So here when we talk about voltage divider, so let us consider this is VCC, which is connected to R1, which is connected to R2, and R2 is connected to ground. So here it is R1, here it is R2, and here it is VCC. So voltage across R2, from voltage divider theorem we can say that is VCC into the voltage resistance across which voltage is to be measured, that is R2, divided by total resistance in the circuit R1 plus R2. This is according to voltage divider theorem. So here it is VR2 is equal to VCC into R2 upon R1 plus R2, and we know the values of VCC. VCC is given, that is 15, into value of R2, that is 5 kilo ohm, that is 5 into 10 raised to 3, divided by, here it is R1 and R2. R1 is 10 into 10 raised to 3 plus R2, that is 5 into 10 raised to 3, and that is equal to 5. So one thing we got, that is voltage across R2, or we can even say that is a V2, that is equal to 5 volt. Using voltage divider theorem we can find out. So important thing to note that when voltage across R2 is say 5 volt, so if we consider this loop A, B, E, D, F, A, so this is the volt at point A, so that must be equal to the voltage VBE plus voltage across RE. So from this figure we can say that from this loop, that is voltage across R2, that is V2, is equal to VBE plus IERE. So from this we can say that IE is equal to V2 minus VBE divided by RE. So we already know the value of V2. VB is 0.7 volt, that we know, and RE is given. Just putting the values, we get 5 minus 0.7 divided by 2 kilo ohm, that is 2 into 10 raised to 3, and that is equal to 2.15 milliampere. So this way we got the value of current IE is equal to 2.15 milliampere. See how did we solve it? We know this is a closed loop, and if we apply Kirchhoff's voltage law, okay, so that is summation of all the voltages in a closed loop is 0. So this voltage is exactly equal to this voltage plus this voltage. So that we got. Now see from figure we can say, so if you look at the figure, here it is, if we see this branch and applying Kirchhoff's law, we know that VCC is exactly equal to voltage across this resistance, that is ICRC, plus voltage across collector emitter, that is a VCE, plus voltage across this resistance, that is IERE. So we can write from figure we can say VCC is equal to ICRC plus VCE plus IERE. Remember that this voltage is equal to voltage across collector resistance plus voltage across collector emitter terminal and voltage across emitter resistance. So from this we can say VCC is equal to VCE plus ICRC plus ICRE. So note that we have considered this IE is equal to IC since IC is nearly equal to IE, because of IB is very small. We know that IC is equal to I is equal to IC plus IB, but base current is very small, so we can consider that IC is nearly equal to IE, and so therefore from this we can say VCC is equal to VCE plus IC common RC plus RE. Okay, now here see, or we can say voltage across collector emitter is equal to VCC minus IC into RC plus RE. So here see, when, let us consider when IC is equal to 0. So when collector current will be 0, remember that when there is no base current flowing, this diode will be not conducting. So therefore collector current will be 0. So when collector current will be 0, this resistance is very high, and remember that the total voltage VCC appears across VCE. So we are talking about obtaining these conditions. See, when collector current is 0, okay, so the maximum voltage we are getting, that is VCE is equal to VCC, but when IC is 0, okay, and when IC is maximum, that means when it is fully forward biased, at that time, that means when this voltage is 0, collector current is maximum. So when IC is equal to 0, VCE is equal to VCC. This locates the first point B on the VC axis. So here VC is equal to VCC. So here we get the first point from this, considering IC is equal to 0. Okay. So when VCE is equal to 0. So see, look here, this is VCC axis and if we consider VCE is equal to 0 this point, okay, so we get maximum current, that is IC is equal to VCC upon RC plus RE, because of when VCE is equal to 0, that means resistance between collector and emitter is almost 0. Okay, so it is fully forward bias, so its resistance 0, there is no potential drop across this, only two resistance RC and RE remains into picture, and therefore the collector current IC is equal to VCC upon RC plus RE. So that is the second point which we get to plot the load line, and by connecting these two points we get the load line. So when VCE is equal to 0, we get IC is equal to VCC upon RC plus RE. Okay, this locates the second point on the axis. So this we get the second point. Now see, we know the value of VCC, RC and RE. So putting those value, that is IC is equal to 15 divided by RC is 1 kilo ohm and RE is 2 kilo ohm. So that is 1 plus 2 into 10 raised to 3, that is equal to 15 divided by 3 into 10 raised to 3, and that turns to be 5 milliampere. So we got collector current IC at the point. So now we can say we have got the collector current IC, that is a maximum 5 milliampere. And second point, so to plot the graph, see here it is. Here when VC is, this is VCE. When VCE is equal to 0, we got this IC, and that is a maximum current, that is IC is equal to VCC upon RC plus RE, and now its value is 5 milliampere that we saw. And here when collector current is 0, we saw VC is equal to VCC, and that is nothing but the 15 volt. But see, actual current in the circuit, that IC is equal to IE, that we know, and that is equal to 2.15 milliampere, that is 2.15 into 10 raised to minus 3 ampere. And we know the relation that VCE is equal to VCC minus IC into RC plus RE. So putting the values, we get 15 minus 2.15 into 10 raised to minus 3 into 1 plus 2 into 10 raised to 3. So therefore we get VCE is equal to 8.15 volt. So here we are getting the value of VC is equal to 8.15 volt. So therefore the operating point Q is at 8.15 volt, and the corresponding current is 2.15 milliampere. So this way we can find out the Q point also. So this is all about this problem. So let us consider another problem of UJT. The UJT is connected across 20 volt DC voltage. So this voltage given is 20 volt. Remember, power supply. The valley and peak points are, valley point is 1 volt, that we already saw in the characteristics of UJT, and peak point, that is 15 volt. The period of UJT relaxation oscillator is 20 millisecond. So remember that we already know that UJT gives us a sawtooth waveform, okay, like this. So here it is, the top is a peak point, and here it is valley point. So corresponding voltage, that is a 15, and here it is 1 volt. So that things are given. And the period of UJT relaxation oscillator, that means one cycle is completed in 20 millisecond. Okay, so the period of UJT election oscillator is 20 millisecond. Find the value of charging capacitor if the charging resistance value is 100 kilo ohm. So this is 100 k ohm resistance, and we have to find out the value of this capacitor. Okay, so that is what the problem is. So the given things are, first thing here it is, sorry, instead of VCC it is voltage between B1 and B2, VBB. So given things are VBB is equal to 20 volt, peak voltage VP is given, that is 15, then R in this, remember that this resistance capacitor decides the frequency or period of this oscillations. So VP R is equal to 100 kilo ohm, it is given, that is equal to 100 into 10 raised to 3 ohm. So T is given 20 millisecond, or that is nothing but 20 into 10 raised to minus 3 seconds. So we know the peak voltage of UJT is given by, so that is a formula which we have already studied, that peak voltage VP is given by VP is equal to eta times, that is intrinsic standoff ratio, that is VBB plus this voltage VD. So here it is voltage across diode, that we know. So here in the problem VD is given, that is 0.8 volt, that is also given, VD 0.8 volt. So putting the value, we get VP is 15 volt, which is given, that is eta, into VBB applied, that is a 20 volt plus 0.8 volt. So from this we can find out intrinsic standoff ratio eta is equal to 15 minus 0.8 divided by 20, and that is equal to 0.71. But we know what is intrinsic standoff ratio relation. So we got this. So the period of UJT relaxation oscillator, that is period T, is given by value of resistance into capacitor into log of, natural log of 1 upon 1 minus eta. So here we know the value of R and C and eta also. So therefore we have to find out the value of capacitance C. T is also known. So C is equal to T upon R times ln 1 upon 1 minus eta, that is equal to 20 into 10 raised to minus 3 divided by resistance R, that is 100 kilo ohm, that is 100 into 10 raised to 3 into log of 1 upon 1 minus value of eta, that is 0.71. And so therefore calculating, we get C is equal to 0.162 into 10 raised to minus 6 farad, or that is equal to 0.162 microfarad. So this way we can find out the value of capacitor. Okay, so thank you very much. Go through the problems and practice. I wish you all the best. Thank you. Bye.